Everybody, welcome. Yeah, welcome to this week's seminar. So this week is Sophie Zegers from here in Prague, the Charles University, and she will speak about the classification of quantum lens spaces.
Yeah. Thanks for the introduction, Ree. So, in this talk, I will talk about quantum lens spaces, and we will look at some classifications results about them. So this is joint work with Thomas Gottfredsen. So before going into anything else, let me define what I mean by a quantum lens space. So here we just start with the lowest dimension. So I think all of you know this very well studied quantum sphere by Waxman and Soppelmann. So here I just look at the tree sphere. And then a quantum version of the tree sphere is here given by taking a parameter q between 0 and 1. If I can point. Okay, between 0 and 1. And then this C of SQ3 is the universal sister algebra generated by two elements, Z0 and Z1, and then it has to satisfy the relations here. And as you see, if you let Q be 1, you are just back in the classical case having continuous function on the sphere. So these relations come from the fact that, so in this case, SQ3 is actually Voronovich SQ2 group. And if we go for higher, up to higher dimensions, then the quantum sphere are defined as some subalgebra of Voronovich SQ n plus 1 group. But I will come back to that. So the relations here comes from, so the relations here, they comes from the relations in this quantum group. And then by Hong and Szymanski, it was proved that these quantum spheres, they can be described as a graph sister algebra. And in this particular case, where the dimension is 3, it's just the graph I have written here, but I will come back to that. Yeah. Okay, so classically, we define a lens space by taking two positive numbers, M0 and M1. And then we need the condition that the greatest common divisor between Mi and R, which will be the order of the acting group, has to be 1. This is because otherwise the this action I will define will not be free. So in the classical case, we always have that the greatest common divisor will be 1. And this condition here will become important when we look at the quantum lens spaces. Okay, so now these classical lens space is defined as the quotient space of this action of this finite cyclic group of order R, and it's given like this. So for Z0, you multiply by theta, which is a generator of the group, to the power of M0, and similarly for Z1. Yeah, and so theta is just a generator of this Z mod R. Okay, so now we can, just in complete analog with the classical case, we can define an action of this finite cyclic group on the quantum tree sphere. So you see the action is precisely similarly as before. And then we define this quantum lens space written like this as the fixed point algebra. And this is an action because if you use these two, theta to the power of M0, Z0, and similarly here, and put them into the relations, you see that they also satisfy the defining relations for SQ3. Yeah, and again, we think about this LQ, this quantum lens space here, as a virtual space. But in the quantum setting, we are allowed to have that the greatest common divisor is different from 1. It's no problem here. And this is just to give you a taste of how the graph looks like. So here, for example, if we have just the lowest dimension and we have R equals 4 and the parameters are just 1, both of them, then you will get a graph like this. But I will come back to how to describe them in details. Okay, so now a natural question is to ask, when are these quantum lens spaces isomorphic? Because we have our parameters showing up, we both have R, and then we have this set of weights. So under which condition will the sister algebras actually be the same? if we change the parameters? That's the main question. Yeah. Okay, so now just a very quick reminder of the definition of a general Waxman and Solomons quantum sphere. So again, we have this parameter between 0 and 1. And then we have n+1 generators satisfying the relations here. And then, just as I explained before, we can also define quantum length spaces for any dimension. So here we take, again, this set of weights, I will call them that, m0 to mn. And then we have an action on SQ2n+1 like this. And then we can define the length space as the fixed point algebra under that action. Yeah, and in this talk, I will refer to this 2n+1 as the dimension. So we will look at dimension 3, 5, and 7. Yeah. Okay, so yeah, the question is under which condition are two quantum length spaces isomorphic? So I will first describe for you how to realize quantum length spaces as graph system algebras. And then we will look at a classification result of graph system algebras over finite graphs. And in the end, I will use that classification result to give you a number theoretic invariant for these quantum length spaces of dimension 7. Also dimension 3 and 5, but it follows from dimension 7. Okay, so let me give you the definition of a graph system algebra first, because everything we will be doing will be on graph system algebra. So yeah. Okay, so we take a directed graph. So here we have the set of vertices is 0 and the set of edges. And then we have the range and the source map. The source map tells you where an edge starts and the range map where it ends. And then we define this, the system algebra, the graph system algebra of the directed graph as the universal system algebra generated by a family of mutually orthogonal projections, meaning that if you take PV times PW and W and V are not the same, then you get 0. And then also a set here of partial isometries, and they have to be indexed by the edges and the projection by the vertices. And then they have to satisfy some relations. So just let me recall that by a partial isometries, you can define it in different ways. But one of them is that this is a partial isometry if SE star SE is a projection. And equivalently, SE star is a projection. So it has to satisfy first that you have SE star is F should be 0 if E is not F. And then you have the rest of the relation which captures the structure of the graph. So you see that this first one here, SE star SE, is the initial projection, and it has to be equal to the projection corresponding to the range of E. Then you have that this is SE star SE, sorry, SE star has to be a subprojection of P and then the projection corresponding to the source of E. And then the last relation says that if you sum over all these projections here, such that the edge starts in V, then you get back PV. And this is true if you have that all the edges going out of E, either you have finitely many and it can also not be non-empty. So for example, if we take this, this very simple example over here of a directed graph, then we see that SE star SE will just be PV, but also here we only have to sum over one edge, so we also get that PV is SE star. So in the end here we obtain that this partial isometry is actually a unitary, so this is the universal system algebra generated by one unitary, which is isomorphic to continuous function on the circle. Yeah. Okay, so what is very useful to have a graph system algebraic description is, for example, that you can calculate very easily the K-theory, K-homology. You can also describe the ideal structure just by looking at the graph. And then we have this very important classification result due to Eilers, Rostov, Ruiz, and Thompson, which says that you can completely classify all unital graph system algebras. I mean, unital is the same as the graph having finitely many vertices. So if you have a unital graph system algebra, it's completely classified using something called the ordered filtered reduced K-theory. And we will not use that because in our case, everything boiled down actually to some matrix calculations, but I will go back to that. Okay. So lens spaces, they are defined as fixed points algebra of the Waxman-Zerbelmann's quantum sphere. So let's first recall the description of Waxman-Zerbelmann's sphere as a graph system algebra. So here we have n+1 vertices, and then we always have an edge Eij if j is greater than or equal to I. So just like here, we will have that n equals 3. So we have four vertices, and then we only have edges going in this direction. And you always have a loop attacked to each of them. Yeah. And due to Hong and Szymanski, quantum spheres are described as a graph system algebra for this graph. And this is not here, that this is actually for Q between, also including 0, which might be a bit surprising here, but they are all isomorphic. So which also shows that all these quantum spheres, they are isomorphic. They have the same graph description. Okay. Yeah. So now let's go to the quantum length spaces. So we have this isomorphism here of the sphere with the graph. And this is given explicitly, which is very nice here, because then we can translate this action we have of this finite cyclic group on the sphere to the graph system algebraic description directly using the isomorphism. And then the action becomes this. So it the projections are just mapped to themselves. And then for the partial isometries, you get this theta, so the generator of Z mod R, multiplied to the power of mi. So it depends on the first of these entries. Yeah. Okay. So now we can describe the length space here as a fixed point algebra of the graph system algebra instead of the quantum sphere. And I'm using the same notation here for the action on the graph, in the graph picture than I did over here. So. Okay, so now the question is, can we describe this fixed point algebra as a graph system algebra by itself? So that's a result by Crisp, which says that this fixed point algebra here is isomorphic to the corner of another graph system algebra. I have not given you the definition. I will give you an example of it, so you get an idea of what it is. But then everything boils down to showing that this corner here of this another graph system algebra, you don't have to understand it yet. I will explain it for you. Is actually a graph system algebra by itself. So that's the problem showing this. And this was then proven to be a graph system algebra first in the case where the greatest common divisor is 1 for all I by Hong and Szymanski. And then later on, Brzezinski and Szymanski, they came up with a suggestion for a graph and also a proof where you don't need this condition of the greatest common divisor being 1. But it turns out that this was not always true. In some cases, it was not the correct graph. And also there was a problem with the proof. And this was pointed out to us by Efron Ruiz. So actually we were doing these classification results and we already had our results and our paper. And then this mistake was pointed out. So we needed to go back to the description and the proof and try to do it again and modify the graph. And we did that recently. So we modified the graph, which was already suggested by Brzezinski and Szymanski. And we also needed to modify the proof a lot. And then we proved that this corner here, meaning that the quantum length space is actually a graph system. And you can see that I have two different notations. So here I have L with a bar, which is our notation, and then I have L without a bar. But the point is that if the greatest common divisor between the first weight and R is 1, then they are the same. So in the case where the greatest common divisor between M0 and R is 1, the graph given by Brzezinski and Szymanski was actually correct. But if this is not the case, you have to modify something. Yeah. So this was just to give you an idea of what has been done. So let me go into the description of these graphs here, but because I think this is, of course, a bit abstract. So I will not give you the definition. Instead, I will give you some examples. I think it's easier to understand them. So if we take n to be 1, meaning that we are starting with SQ3, then we let R be 4 here, and M, the set of weights is 1 and 2. So then the way we construct this graph here, which is called the screw product graph, is that you take, you can look at it as you have two vertices describing for the graph describing SQ3. So you have two generators and you have two vertices in the graph, this graph L3 describing it. So we have, which means that we will have two levels. So the number of levels depends on the dimension. So here we'll have two levels. And then R tells you how many vertices you have on each level. So here we have 4 of them on each level. And then M indicates how you have to go around and draw your edges. So for example, here you will have an edge because you just add M0, which is 1, and you add it again and again. But here you get 3, and if you add one more, you get 4, but that is congruent to 0 modulo R. So you have to calculate everything modulo R. And then if you go from this level to the next level, you have to add M0. So you have to add the number which corresponds to the weight coming from the level you are starting in. So here you also add 1. But in the second level, you see that here you have to add 2. So if you add 2, then you come back again. And the same here, if you add 2, you come back again. Okay, so a very big difference, because from having that the greatest common divisor is always 1, and here allowing that it's not 1, is that here you can get those 2 cycles here, and here you only have 1 of them, because the greatest common divisor is 1. Yeah. Okay, so let me just explain it in greater generalities. So in general, you will have n+1 levels. You will have R vertices at each level, and then you have an edge coming from Vik to Vjk plus Mi, and you have to calculate everything modulo. And then the greatest common divisor between Mi and R tells you how many cycles you have on each level. Here you will have 1, and here you have 2 of them. Okay. Yeah, and just to recall for you, the reason why we need this graph is because the length spaces is described as a corner of the graph system corresponding to this graph. So that's why it's important. So let me now describe how you obtain the graph for the length space, which I have over here, from this graph here. So what you do is that you have to look at some specific paths in the graph. So what you do to begin with is that the orange, the vertices I have marked here in orange, you have to take them over here. You can see we have V00, V10, and V11. So they are corresponding to 1 vertex on each of the cycles you have. Okay. And then you have to start counting some specific paths. So the number of edges between V0, 0 and itself is 1, because you can, in the graph over here, you have one path from this vertex here to itself, not going through that vertex again. Okay, they are not allowed to go through the orange vertices, but then you would also have infinitely many. Okay, so that's why you will have this loop over here, similarly here and here. But then if you have to look at the number of paths from V0, 0 to V1, 0, then you will have 2 of them. You can just, let me see, you can go down like this, or you can move 2 steps here and then go down here. But you only have 2 of them. That's why you will have 2 edges over here and similarly here. Okay, so you have to, so to obtain the graph for the lens spaces, you have to count number of paths. And I think you can imagine that if the dimension grows, you get more levels. And if R grows, you have to count a lot of paths. Yeah. Okay, so in general, you have that this graph over here has n plus 1 levels. It always has one vertex at level 0, which is the main difference from the description by Brzezinski and Szymanski. That was actually where the mistake was. But you will always have this, and it comes from the fact that you have this corner. I will not go more into the description as the corner. And then if we say that the greatest common divisor between M0 and R is 1, then it has the number of, then it had this number here, vertices at each level. So here you see that the greatest common divisor between M1 and R is 2, so you will have 2 vertices here, and here it's 1, so you have 1. So the greatest common divisor tells you how many vertices you have on each level. And then the number of edges corresponds to the number of something called admissible paths, which is just what I described to you. You have to look at all the paths, not going through the edges marked here. The vertices are marked in orange. Yeah, so that's how you have to construct it. And again, I will not give you general definition, but I hope you have an idea of how you construct them, at least in the lowest dimension. Yeah.
How comes that this does not work for Q that goes to 1?
Yeah, you mean if you don't have this yeah. So what was wrong in their proof was actually that. So then we have to go a bit back to the description as this corner, because the corner here we mean that if we look at this graph, then you take the corner coming from the projection corresponding to VI0. So let's go back to the example. So you have to take corner corresponding to this projection and this projection here. Okay. So if you have that the greatest common divisor is not 1 for the first one, then you will have maybe, let's say you have 2 cycles here. Let's say it's 2, so you have something similarly as here. But then you can never go from V00 to V11 or V13. So when you look at the corner and you have your when you take the corner by that projection, and if you cannot go from any of the vertices corresponding to that projection or the projections, then it's not in the corner. So you simply have to remove that part of the graph if you have some cycles over here. Yeah, more than 1 of them. Okay, that's the rough idea of it. So things becomes a bit more complicated if you have maybe 2 cycles here, and then if you have it below here, then you can see that you lose some things in the different steps when you take the corner. Yeah. Was it okay. It's just an idea, because in the proof you have to go through a description by Ackling and Efron Ruiz, so where they actually describe a corner of a graph sister algebra as a graph by itself, but then you also need some classification results in the end. So the isomorphism is not explicit. Yeah. Okay. Okay, so are there any other questions for the description of the graph? Okay, but then I will move on to this classification result of graphs, C star algebras over finite graphs. So as I said in the beginning, they are actually completely classified if you just have a unital graph C star algebra, meaning that you have finitely many vertices. The edges, the set of edges don't need to be finite. But now I'm just assuming that the graph is finite, which is the case for the length spaces. But everything they have been doing has also been extended to just unital graph C star algebras. But let's just assume that the graph is finite. So as I said in the beginning, they can be classified by something called the order reduced filter with K-theory. You have to look at the K-theory of all ideals and quotients, and then you have to look at maps between them, so it becomes very complicated to actually work with. But then we are in a very good situation here, because we have, first of all, we have a finite graph, and we are, from now on, I will just assume that. But then we also have that the length spaces here, they satisfy this condition, saying that it has no vertices which support two distinct return paths. It means that if you have a vertex, you cannot go through two different paths in the graph and come back to it again, and they have to be distinct. You can use the loop, and you can, of course, use it many times, but then the different turn paths, they will not be distinct. So if you remember, the only way you can go back to the vertex is using the loop. Okay, so length spaces, the graphs, the description of the length spaces satisfies this condition here. And this condition is the same as having that this graph C star algebra is something called type 1. But I don't need to go more into that. If we know that the length spaces fits into it because we know that the graph satisfies this condition here. Okay, so now we have the theorem. So first I have to say that AE denote the adjacency matrix, just telling you how many edges you have between your vertices, and then you put it into a matrix. And then we have another matrix, BE, where you just subtract the identity matrix. Yeah. Okay, so the theorem says that if you have two graphs, E and F, they have to satisfy the condition here. And if they are in something called standard form, then the graphs, the algebras will be isomorphic if and only if we can find some specific matrices such that this is satisfied. I know that I need a lot to explain you a lot here, but you can see that if we understand what a standard form is, we understand what these matrices are, then everything you just have to do is actually to solve a set of linear equations here, and then you can then I can tell you if the length spaces are isomorphic or not. So it's a very powerful tool when you are in the setting of the C star algebra being type 1. Okay, so this little E wedge here just means that you have to add a loop to all things in your graph. We don't have any things, so you can just avoid it. Yeah, just some technical things. You see here we have to subtract the identities, so it makes sense that you don't want to have any negative numbers in your matrix. Okay, yeah. Yeah, I will explain it now. Yeah, yeah, but that's a good question. Yeah, right now I have not given any description of the matrices, yes. And being in standard form, I will give you a rough idea of it, but it's a very long and technical definition in general. But I will translate it to this quantum length setting. Okay, so this SLP is defined by taking a partially ordered set such that if I is less than j in that order, then I is less than j in the natural order or the usual order on the natural numbers. So it has to satisfy that condition, otherwise it's just a partial ordered set. Then we look at this MP, which is the set of all upper triangular matrices, n times n matrices, which has to satisfy this condition here. So the order determinants where you can have zeros in your matrix. So your entries are aij has to, if it's different from 0, then you need I to be less than j in that order, in the partial order. And then SLP are just the matrices where the diagonal consists of 1. And maybe you're wondering why we have this bold 1. So it means it's because you can also extend this. In our case, you just have that the block structure is just 1 times 1, but you could also have another block structure. So the 1 here just indicates that the block structure is 1 times 1. So it's the easiest way you can have it. Yeah, I will give you an example in a minute, because now what has this partial ordering anything to do with the graph system algebra? And here we have to look at something called the prime and gauge invariant ideals of our graph. So I will not go into the details here, but gauge invariant means that you have you have this natural circle action on your graph, where you just have your partial isometries are mapped to some element in the circle times the partial isometries, and the predictions, they are fixed. So it has to be invariant under that, and then we are looking at something called some specific ideals which are prime. But it turns out that this space here of all the proper ideals can be described just by looking at the graph. And I will come back to that. But the point is that you have to choose this partial ordered set such that you have an order reversing isomorphism between the set and this space of these ideals. And then you need this BE and BF to be in that specific MP. Yeah, I think it will, yeah. It stands for gauge invariant. Yeah, so the gauge action is usually denoted gamma. Yeah. Okay, so I think this will make more sense just by looking at an example. But I hope you see that this explains how you get from what this partial order has to do with the graph, because the partial order has to capture the ideal structure. So that's the point, but I will show an example. So first of all, as I said before, this P has to be chosen such that you have an order reversing isomorphism between the space of those ideals and P. But this space here can actually be described as something called the component poset. I should say that those two spaces, they are topological spaces. You can put a topology on them, and they have to be homeomorphic. Okay, so what is the space here? So this component poset consists of the maximal connected components of the graph. For the length spaces, it's very easy to describe, because you have to, a connected component means that if you have two vertices inside that subset of the vertex set, then you can always find a path between them, so going in both directions. Okay, but in the graph here, you see that if I wanted to look at some connected components here, I can only choose the singletons. If I took both V1 and V2, there's no way I can get from V2 to V1. Okay, so all the elements inside this component poset for these length spaces here are just singletons. Okay. And then they order it like this, saying that gamma 1 is greater than gamma 2 if you can find a path from a vertex inside here, meaning V1, to a vertex inside here, this one, meaning V2. You can find here one from V1 to V2, so you have this order here, and 1 to 3, so we have this order here, and nothing else. Okay. Okay, so now we have to relate it to a partial ordered set. We can just choose one. So I take this P to be 1, 2, 3. I say that 2 should be greater than 1, and 3 should be greater than 1, because then we get very easily a map from P to this set here, just by mapping I to gamma I. So the way we did it for these lens spaces was to, you look at the graph, you have the order of these component poset, and then you just reverse everything. And then you will have this P with the order. Okay, so you build your partial ordered set from the component posets, and the component poset captures the structure of those specific ideals you want to look at. Okay. Okay, so there's one more thing here. We need to have that BE and BF, so the two graphs we're looking at, has to be in this MP. So it means that you can, if you have a graph, you can write up your adjacency matrix in many different ways. Here I have just, this is not the most intuitive way, but if I took V3 first, then V1 and V2, the matrix will look like this. So here we have that there are one edge from V3 to V3, two from V1 to V3, and so on. But then we see that using this order over here, we cannot have two here because this is A to 1, and 2 is not less than 1 in the order over here. Okay? So I have to write my matrix in another form, and now it's more intuitive. And if I do it like this, I get precisely that this BE, where you subtract 1 from the diagonal, is inside this MP. And a general element in SLP will look like this. Okay, so you see that the point here is that the structure of your adjacency matrix captures the structure of those specific ideals we want to look at. So if you have two different graphs, of course you need the component poset, or this prime set here of this prime gamma, to be homomorphic. If you want to have isomorphic graphs, these algebras, you need that those spaces are the same. So that's where you start. And then you have to see if you can choose, you have to look at the ideal structure, and then you have to choose some order, which tells you how your adjacency matrix should be. So very simple set, if you have the two graphs and you can order the adjacency matrices such that they look similarly, then you can start comparing them. And that's what I mean by having this BE and BF in MP. And that's also what we mean by having this standard form. Okay, so it's a lot of preparations you have to put on this, considering the ideals and then writing up your adjacency matrix in that specific form, and then you can start using the theorem. Okay. So are there any questions to that? Okay. So let's go back to the theorem. And let me translate the theorem into the setting of the quantum lens spaces. So being in standard form here boils down to having that greatest common divisor. You can look, if you have two graphs and you have the different levels, then you want to have the same number of vertices in each level, because otherwise the ideal structure cannot be the same. Okay? So it means that you need the greatest common divisor to be the same for Mi and Ni. If we have two lens spaces where the N describes one lens space and M the other one, and I is fixed. So this is what standard form boils down to here. So then we can say that these two lens spaces here are isomorphic if and only if we can find matrices in this SLP. Of course, you have to choose P, but it's possible here, such that this is true. Yeah. Okay, so what we did was first to look at a lot of observations in a computer program in Maple, which was made by a system from Søren Eilers. So as I said in the beginning, you have to look at all those paths in the graph, which becomes complicated very fast. And then you have to solve this set of linear equations you get from this part here. So it's very natural to start doing it with a computer and check if you can find a system. So that's what we did. And after that, we, of course, had to do everything by hand. So first calculate the adjacency matrices, and then apply this by SLP equivalent. I mean this, calculating this set of linear equations and finding a solution. So that's the procedure. But the observations we did using the computer was very crucial, because it's very easy to make mistakes with all those calculations. So it was a very important tool. So let me describe some of these classification results for you. So first of all, when Arlos, Westerf, Ruiz, and Sørensen, they wrote the first paper on this classification of the graph-system algebra, they have these length spaces as an example, but in the case where the greatest common divisor is 1 for all the I. So meaning that in the graph, you just have, at each level, you will have 1 vertex. And here they found out by just the procedure I said before, that for dimension 3 and 5, meaning that you're looking at SQ3 and SQ5, here all the length spaces, they will just be isomorphic. And if you have length spaces of dimension 7, then we start seeing some differences. So here we have that 2 length spaces of dimension 7, they are isomorphic if this condition here is satisfied. So maybe it does not tell you so much, but you can see that you can actually just plug in the numbers, and then you know if they are isomorphic or not. So
does this, how does this relate in the classical case? I mean, are you getting
I will
isomorphism?
give you some examples of that of that also. Yeah, but a good question. Yes, I have some examples to point out there. Yeah, but let me first say that from this result here, you can say that if 3 does not divide R, it has something to do with number 3 you have here. Then all the quantum length spaces, they are all isomorphic. So yeah, they're all isomorphic. You can also say they're all isomorphic to the one where you have just 1 everywhere. And if 3 divides R, then you have 2 different classes of length spaces, depending on whether M1 is congruent to M2 modulo 3 or not. So you only get 1 class if 3 does not divide R, and you get 2 classes if 3 divides R. Yeah. Okay, so I have a bit on the classical situation here, just to compare them. So classically, we have that these 2 spaces here, they are homomorphic. But if we compare with the case we just looked at, we see that if 3 divides R, it does not agree with the quantum case, because here, this is precisely the 2 parameters we have here. And we also know that if you take just any set of weights here, then it's all the space here is always homomorphic to the space where you just have 1 on all of them, if and only if R is one of the numbers here. So it means that if 3 divides R, it does not agree with the quantum case again. And if R is greater than 4 and 3 does not divide R, it also not agrees with the quantum case. So yeah, the comparison shows here that there are actually some main differences between the classical and the quantum case. Yeah, so that was just a small mark here. So I want to just spend some minutes on what I did with Thomas Gottfredsen, because I just showed you how the length spaces were classified if you assume that this greatest common divisor is 1 for all of the weights. But now we are assuming that one of them are allowed not to be 1, only one of them. Already here, things becomes much more complicated, and the calculations becomes much longer. So we are starting with just assuming this for one of the weights. So then we can be in these 4 different cases. So depending on which of the weights has greatest common divisor, not 1. So remember that it was a bit special if you have that the greatest common divisor between M0 and R is not 1. Here it always looks like this because of this corner you take. If you, yes, sorry, yeah, I think I know what you will see. Yeah, I should say here, yeah, thanks for pointing it out. Here I'm just indicating that we have some edges, not how many we have. Yeah, so it's, yeah, this is just to say that there are some edges, but not how many. And exactly, it's not the sphere. It's not the sphere. You have more than one here, but you always have a loop, and you always have minimum one edge. Yeah, but it's not the sphere. Yes, it was just too many edges to draw. Yeah, but everywhere there should be some number, and not only one. Okay, and if we have that the greatest common divisor between M1 and R is K, then we know that we should have K vertices on the second level. For this one, you should have K vertices on the third level, and here on the last level, FM. Okay, so the graphs looks like this, and you cannot have that a length space from different boxes here are isomorphic, because the ideal structure will not be the same. Okay, so we have to just classify them in each of these cases. So I will take a closer look on this one here, and it's only to give you an idea. I will not go through any calculations, but I will show you how this adjacency matrix looks like. So in this case here, as I said, we have the greatest common divisor between M3 and R is some number K. And then the matrix looks like this. So the first part here looks nice, and we have this identity here, precisely because you don't have that these vertices here are related, the last ones. So that's why you get identity here. Okay, so now the question is, what is this X and Y? And it looks like this. So yeah, so you don't have to look closely at it, but it's just to give you an impression of how difficult it is to calculate. Because remember that the entries in this adjacency matrix correspond to a number of paths in this big graph. So you have to calculate all the paths and make a nice formula for them. So it looks like this. And you see you have a lot of sums involving something calculated modulo K or modulo R or something like that. But it is possible to do it. And that's also the reason why we have only assumed that one of the weights is not 1, because otherwise it grows bigger and becomes even more complicated to write up. But we have done something similarly as this in all of the 4 cases here. And then I can show you the result. So if you take 2 length spaces, we have 2 different set of parameters here. We have to assume that one of the greatest common divisor is something which is not necessarily 1, and the rest of them has to be 1. Then they are isomorphic. In this case we just looked at, if and only if it satisfies this condition here. Maybe you remembered it from the case where the greatest common divisor is 1. This was precisely the condition they had. And then you also have that Mj and Nj for j equal 1 and 2 has to be congruent modulo that K, which is the greatest common divisor. So you get some extra conditions. And if you look at it, it also makes sense, because if K is 1, this is always satisfied. And then we are back with this first condition. And again, so here, if you look at the 2 other cases where you have the greatest common divisor is different from 1 for M2 and M1, then you also get this condition here. For M1 here, you can see that you have just changed the role of 1 and 2. So in this case here, N2 has a multiplicative unit, but M and N1 does not, because the greatest common divisor is not 1. So it looks like this, and then for the last this last cases here, we just have the condition from the case where the greatest common divisor is 1 for all of them, and otherwise they're always isomorphic. So maybe this does not tell you that much, but you see that it's an extension of what was obtained for the case where the greatest common divisor is 1 for all of them. But the calculations and the structure of the graph becomes substantially more complicated in the case. So this is just to give you an idea of how many classes we actually have. Maybe it's more interesting than looking at this condition before. So if we let this set K, this here be the group of all the units, so every element in set mod K, which has a multiplicative inverse, then we see that if we'll have that the greatest common divisor between M3 and R is K, then you get the number of elements in the group of units to the power of 2 and twice as many here and the same here. So depending on the conditions here. And here you see that you get the same for if I is 1 and 2, but for the last case here, you have something similar as the case where the greatest common divisor is 1 for all of them. Yeah. Okay, so let me just say a few words about dimension 3 and 5. I have only mentioned dimension 7 for you, and then I said that if the greatest common divisor is 1 for all of the weights, then you get that they are isomorphic for dimension 3 and 5 just by looking at the graph. The graph is the same for them. Okay, so in our case, if we allow one of the weights not to be the greatest common divisor for one of the weights not to be 1, we again obtain that for dimension 3 they are all isomorphic. For dimension 5, we get we are in 2 different cases here. So if I here is 0 or 1, they're again all isomorphic. If it's 2, then you have a condition here which looks like that extra conditions we have for dimension 7. And then one more thing to point out, I have fixed R through everything. But we can also show, knowing the adjacency matrices and using the classification source, that R is an invariant in all cases except in dimension 3. And the reason is that if you look at this example here, we have in generally that the adjacency matrix, if you have M0R as K, this greatest common divisor as K, looks like this. So for example, if you take R to be true and those 2 parameters here, you get the same as if you take R to be 4 and those 2 parameters here. So something else happens in dimension 3 where this order of the acting group is actually not an invariant, but it is in all other cases. It's only in dimension 3 you see this behavior. Okay, just a very quick word about what I'm doing now, because now we have been looking at isomorphism between quantum length spaces. And what I'm working on with Søren Eilers now is to see if they are also equivariant isomorphic, meaning that so you have a naturally circle action on the quantum sphere, you can put it on your length space then, and then you can ask if you have 2 length spaces which are isomorphic, are they isomorphic in a way that preserves that action? And here we are looking at dimension 3, we know they are all isomorphic, and now the question is, are they isomorphic in a way that preserves the action? Yeah, but that will be for another talk. Yeah, that was everything. Thank you.
Questions from the audience or
Actually concerning isomorphisms of length spaces. So classically, I think 2 length spaces are easy examples of 2 manifolds that can have the same homology and fundamental group, but being not homomorphic. Is this related to the last question that you presented?
Good question. We have not looked into if we can relate that last question to the classical case, but it's something we also are considering. Yes, if there's some relation, taking into account that extra structure of having the action. Yes, but I don't have any answer right now.
Thank you.
any more questions? Yeah.
4 classes when you had 4 graphs.
Yes.
Right.
Oh,
Oh, yeah,
this
yeah,
one,
this
yeah.
one. So as you mentioned, so the picture is schematic because you did not indicate all the edges, but is it the case that the graph from the upper left corner is embeddable into the remaining 3 graphs?
So if you want to, so embeddable, you mean something like taking the quotient, something like that, or just like graphs? Okay, so in the case here, if you think about it as a graph system algebra, and you want to maybe look at some quotients or something, then you have to remove vertices like this in the graph, and then it would not be. So it's not like the sister algebra here is embedded in some quotient of the graph sister algebra over here, because you have to remove vertices from below and up corresponding to the ideals if you want to look at quotients by some specific ideals. But I don't know if there's any, maybe you're thinking about when you're counting the edges or something like that. We don't see any relations in the counting or in the adjacency matrix between those cases here, because when you have when you look at the big graph, then you have k+1 cycles here, and it has a lot of it means a lot when you have to count the paths, because then you already go through some cycles at the second level, and here on the third level, and here on the last level. I don't know if it answered the question. Okay. Yeah.
So any questions more from the audience or from online? Is there anybody raising their hand? I mean, if not, Bob.
No, it's just to say hi, but and thank you for the talk. But I'm sorry I missed almost all of it, but I got in for the last 15 minutes, so at least got an idea of what you're doing, which looks great.
Then in that case, I'm going to go back to the question that I had earlier on about what happens
Oh.
in the comparison with the classical case, because I'm not too sure I totally got it. So are you saying that you have...
So those are some results I found about classical length spaces. And then I don't see any, it's not like I have any pattern between the quantum case or the classical case. It's just a comparison saying that classically, those 2 spaces will always be homomorphic, but this we know is not the case if 3 divides are, because then this results I have here tells us that they are not the same. No, the quantum version, yes. The quantum version, yes. Not the sister algebra, the continuous function on them. No, the spaces here will be homomorphic in that case, but the quantum case of them, the quantum description, it's not isomorphic. Yeah.
I'm just asking a question. We were seeing some flags. Classically, they were not the same as the Easter algebra was.
Easter algebra. Q not equal to 1.
Q not equal to 1.
Q not equal to 1. Yeah. Okay.
So you're getting...
Yeah, that's weird.
I would have expected that you would have had
More isomorphic.
more isomorphic. That makes something would be not the same classically, it would be the same.
Yeah, not the same classically, but the same quantum. But did...
Talking about
Yes. Yeah.
Not in case because the manager is
Yeah.
Yeah.
I would have expected that more isomorphism.
Yeah.
Okay, interesting.
But there's something where they agree and where it's not agree, Also, because here I'm just saying that those two specific ones, I'm not saying anything about some arbitrary, but if you have some arbitrary ones, then here they are always homomorphic. If you have one of those, so if let's not agree with the quantum case. Yeah, so here they will be homomorphic. But if you have 3 divides R, then you get more in the quantum case than the classical case. Because here you get 2 of them. If 3 divides R, then you have 2 different classes. But if R is 3, let's say that. So if R is 3, then this result says that classically they are all homomorphic. But if 3 divides R, so if R is 3 again, you have 2 different classes. So this will be an example where they are all homomorphic classically, but the quantum Lens spaces, here you have 2 classes. Yeah.
And are these ones that don't agree in the quantum case, are they still classical?
I don't know. No, I haven't looked into that. Yeah, but that's a good question. Yeah.
Because they are like quantum spheres.
Okay. Yeah. Yeah. Yeah, so it's also a good question with the KK curlons. So already calculating the K theory of Lens spaces is so yes, in some examples they have been calculations, but not in general. So yeah, that's also something to be understood there. But of course we have the adjacency matrices, so you can try to work out the K theory from there, but it's not that obvious. Yeah.
So are there any other questions in the audience online? Okay, since it doesn't appear to be the case, we'll thank Sophie again. And next week's talk. Next week's talk